Hooray. So, I sent out an email to the class yesterday. I don't know if you've checked your email or not. If you have not, don't sweat it. It's there. I sent it through the Moodle page. But once I start assigning things, I like to send out emails toward the end of every week, just so that we're all on the same page. Like, hey, there's these upcoming due dates. Please be aware of them. Okay, because it's so easy when you have all these different classes to kind of keep things straight. And so I think I'm assuming it's kind of helpful to have that where it kind of puts it all in one place. Okay. And I'm happy to say that there was a request for me to do an example of the homework. I love questions. Okay. So number one, don't forget that 1.1 is due tonight by midnight. Okay. If you have not yet completed it, you have till 11:59 p.m. to do so. And section 1.2 is due next Wednesday by midnight. Okay, so it's my intention that we're going to start 1.3 today. How far we get is, neither here nor there. But the way I always want to start class is by addressing any questions that you may have. And Ross is awesome and asked a question. And so I would like to address that. And well, I think what I'm going to do actually, so I'm not going to share that because, hold on, I'm going to take this off for a second. Okay, because I want to reveal your question, but it's nobody else's business. So this is the last question on the online homework. Yours might not be exactly the same, but it's probably going to be pretty darn similar. And those of you on Zoom, I promise you, you'll see it in a second. And I'm really glad that you asked this actually, because I want to make a comment about this program and the graphing capabilities it has. Okay, and I'm actually going to do that before I even do this. Okay, so you're like, okay, let me see. You can do it. Yay. Okay. So one comment that I want to make about this online homework system, none of them are perfect. They're made by humans. Okay, so right from the get-go, none of them are perfect. There's going to be bugs and glitches here and there. Sometimes the graphing can be so irritating, because they're going to want an open circle, or they're not going to want you to have a circle shown, and it's so hard to get rid of it. So what I want to tell you all right from the get-go is I try to be really mindful about how many graphing problems I actually put in here, because the program can be kind of a pain. But what I want to say is if you feel like you answered it correctly, but it was like a difference of a dot or not, all you need to do is hit message instructor. If you want to take a picture of your work on your sheet of paper and email it to me, it takes me nothing to go in and give you full credit. Okay. So if you feel like it's an entry error and you have the graph, but the program is just being really difficult with you, all you need to do is message me. Okay. So I don't want to make this be a real pain in your side. I'll just make everything else. Just kidding. Okay. So what we want to do is we want to graph this piecewise defined function. Now, one of the things that we saw with these piecewise defined functions is this part is our domain. This tells you which part of your x-axis you're going to be looking at when you're actually plugging in and looking at the various functions. So for example, I'm starting at -1, and this function is relevant for all values of x less than or equal to -1.
Okay, how is my function defined?
-3 on the y-axis.
-3 on the y-axis. Do you agree? I would put a closed circle here because I've got the equal to, and we know that that's a constant function. You with me on this part? Thumbs up, thumbs down. Okay, opinions are great. All right, I'm going to bop over and do this next one now. Okay. So if x is greater than 1, in other words, open circle at 1 on larger, how is my function defined? Isn't it at -1? Okay, so I put an open circle here to indicate that that's kind of my starting point, and it's a constant function at -1. Okay, notice I have an open circle because it's for values of x that are strictly greater than 1. Notice there's no equal to sign. Questions there? All right, so the issue is what happens between -1 and +1, okay? We see that when we plug in +1 into whatever this function is going to be, we're going to have a closed circle because we actually have that equal to sign. And that when we're plugging in -1, we're going to have an open circle because that's essentially going to be our starting point, okay? So if I plug in x equals -1 here, and I'm using this identity function, I always call this the stop copying me function, just because my brother and I used to get in a lot of fist fights when we were little, because like I would always copy him and irritate the heck out of him. Anyway, the reason why I call it that is because whatever x is, y is. So if I plug in -1 here, what comes out? -1. If I plug in x equals 0, what comes out? Well, if I plug in x equals 0, 0, don't be scared. If I plug in x equals 1, remember this function when we talked about our toolkit functions? It's our identity function. Whatever x is, so is y. So if I plug in x equals 1, what's going to come out for y? +1. So it's that diagonal line. Notice it's a good thing I have an open circle in one place because otherwise this would fail my vertical line test miserably. Same thing here. This would fail my vertical line test miserably. So it's important to keep track of where you have your open and closed circles. Does that help?
That's awesome.
You're awesome. Thank you. And I mean that, like, bring them on. It's what makes class fun, is when people are interactive and ask questions. Are there any other questions on your homework in 1.1 and 1.2? Yes. Oh, no. Okay. Anyone on Zoom? Alex, Megan, Finn, and Van, do you have any questions? All right. Okay, cool. Thanks for responding. Okay. Moving right along. So section 1.3, we're going to be talking about rates of change and the behavior of graphs. I always think it's kind of funny to talk about behavior. Right? Telling your graph to behave. Now, I would venture to say that you've looked at these sorts of ideas, especially rate of change, pretty deeply in your past. But we're going to kind of formalize it, and I'm not trying to make anything more confusing or anything.
rates of change are huge, okay? If any of you are going on and taking calculus, rates of change are really a huge aspect of the study of calculus. Okay, and then there's also like area issues that you deal with within calculus, but the rate of change is something that's like one of the main focuses of a calculus study. And I claim we've actually already dealt with the rate of change before, and you actually, at least with a certain type of function, even already have a name for it. Okay, so when you're talking about lines, the rate of change is actually your slope. Okay, but I'll show you how all of that works. So what I want to tell you first and foremost is that the rate of change describes how the output changes in relation to the input. And we look at these things a fair amount. I would venture to say that every time you drive, it's probably wise that you pay attention to your rate of change so you don't get a ticket. Okay, so one of them is miles per hour. Okay. As you continue driving, how many miles have you gone? Another one, which I think really was people were keenly aware of, fortunately until recently, is the number of dollars per gallon of gas. Fortunately, that's decreased as of late. Okay. Miles per gallon. You want to talk about the gas mileage of your car. Okay. You go and you want to compare shopping, you know, like you can buy the same item in different sizes, which is a better deal. Most people think the bigger one is always the better deal. That's not always the case. But, you know, dollars per pound or dollars per ounce, things like that. We look at these rates of change a lot. Notice it's a ratio, it's a fraction. Okay. So what I want to do prior to getting into the actual rates of change is I'm just going to put a very dated example. And I want to just make distinctions between a change versus a rate of change. Okay. So this is the case, but that suppose in 1950, the world's population was 2.555 billion people. And in 1990, the world population was 5.295 billion people. I honestly don't know what the population is currently, but if anyone knows, is it like 7 or 8 billion at this point? It's a lot of people. Yeah, it's a lot of people. I'm happy to be in Montana. All right. So what if I asked you, what is the change in population over this 40-year period? What are we doing here? When you want to know the change in something, what operation do you think we're using? And don't be afraid. If you're wrong, it doesn't matter. You're thinking, and that's the beautiful part. Subtraction. Thank you. Yeah, when we ask the change in population, in other words, how much did the population change? We want to subtract. We want to say, well, it was 5.295 billion people in 1990, and it was 2.555 billion people in 1950. So the change in population was 2.74 billion people.
Thank you. Okay. Now, in case, yeah, I'll just be quiet right now. So when I ask the change, we're just taking the difference between two numbers, okay? We're just subtracting. Now, I want to contrast that with the situation where I would ask you, what is the average annual rate of change over this 40-year period? I'm now asking a different question. It's related. So what's the difference? Well, you see the word average, okay? We're not assuming that in each year of this 40-year period that the change in population was the same, right? Presumably, it, population grows exponentially, not linearly, okay? So average just means like if you're going to look at those 40 years in general. And notice I'm talking about rate of change over this 40-year period. So when I do that, what I'm asking is for the change in population over the change in time. Remember, change, we sometimes use a triangle, change in population over the change in time. Well, we just computed the change in population. What was that? 2.74. Notice that's billion people. What's the change in time? 40 years. Notice I'm including my units because units are super important. Okay. So we could say if we did this computation, it's about 0.0685 billion people per year. Now, this doesn't really mean a lot, but I did some extra computations, and if anybody really cares, that means that it changed by it increased by 130 people per minute. Isn't that fun to put it in those terms? I just changed billion to number and year to minute, okay? So notice when we're talking about the rate of change, we actually have a ratio, okay? All right. So when you talk about the average rate of change, it's the change in the output over the change in the input. Okay. And what I want to say is, number one, these triangles mean change in. It's just a short way of writing it because we don't want to have to wear out our poor hands. Okay. And this is something that should be pretty familiar to you in another context. Okay. Aren't our outputs generally we call them our Y values by default, right? X values, Y values. So translating it to be an XY value, aren't we saying it's the change in Y values over the change in X values? Right? Outputs are Ys, inputs are X's. What does this look like? What is this the computation of? It is division. It is division, but pertaining to a function that we're familiar with. Here. Hangman, give me a letter. Oh, come on. It's the slope. You kept all your body parts intact. Yes. Remember back when you studied lines, and if you don't remember it, it'll come back to you soon. Remember your slope, your M value is the change in Y over change in X. Okay. So when we're talking about lines, this is precisely our slope. Do you guys want to know the coolest thing you're going to hear from me today? Do you want to know the best hangman word ever? Links. Right? Because everyone guesses vowels, A, E, I, O, and U, and it's like, well, they're not there. Anyway, if you don't walk out of this class with one other piece of information, here's a really good hangman word. It's a good thing to know if you ever have kids. Thank you. I like to be useful. God, I sound like my mother. Okay, so let me give you another example. I'm going to do this one. I'm going to make a table because we can show our functions using all sorts of different ways. So I'm going to have 1, 2, 4, 6, 9, and 11. And I'll explain what all this means. So my N, or my input, is the nth day in June. Okay, so like this represents June 2nd. This represents June 9th. And the output is the average daily temperature. And we'll say it's in degrees Fahrenheit on that particular day. Okay, so on June 6th, how hot was it? 99 degrees. Wow, that doesn't sound very fun. Okay, so what if I asked you to find the average rate of change between June 9th and June 11th? Not only that, but I then want you to write a sentence explaining the meaning of our answer. You'll see that that's a really big focus here, simply because we're not just doing these computations because it's fun to do math, but we're actually doing these things because they pertain to real life things. Okay. So how do you find the average rate of change? Well, isn't it your change in your function values divided by the change in your inputs? In other words, don't I want to find D11 minus D of 9 divided by 11 minus 9? You with me there? Change in outputs over change in inputs. What's my function value at 11? 102. What's my function value at 9? 104. What's 11 minus 9? With confidence. It would be 2. Don't be shy, my friends. This is a community effort. Well, what's 102 minus 104? -2 over 2. And what do we get out? -1. So the average rate of change, if we were just doing these computations, we would get -1. But let's add units in. What are the units of my numerator? Yeah, degrees Fahrenheit. And what are the units of my denominator? Isn't it days? Days in June. You got it. So what is this saying? What this is saying in practice is, on average, from June 9th to June 11th, the temperature, did it increase or decrease? It decreased. How do we know it decreased? Because it's negative. the temperature decreased by 1 degree Fahrenheit per day. I know it seems silly and like a lot of work, but there is a lot in this class of interpret things in the context of the problem. And that's usually a long-winded way of saying, use your units, please. Okay. All right. So are you guys okay with this? You're very quiet, so I'm not really sure how to read you yet. Every class has its own vibe. I just want to be sure that you're quiet is because you don't feel like talking rather than you're not understanding. Because if it's that you're not understanding, I would like honestly beg you to please speak up. Cool. Thank you. Thank you. Thank you. Now, we like to talk about the average rate of change, but that's so much writing. Okay, so what I want you to see is that you're going to see some shorthand. This is my lazy person's way of saying average rate of change. Okay, that's going to be a big time thing. All right. Now, so we've done this with a table, we've done this kind of verbally. What does this look like for a function? Well, I'm going to draw just some ye old generic function. Okay. And I'm going to have A be right here and B be right here. Would you grant me that the corresponding ordered pair on this graph is A comma F of A? And right here, it would be B comma F of B. Just throwing in the notation so that you start getting used to it, right? Ordered pairs, input, output. Okay. Now, what if I wanted us to find the average rate of change of this function from x equals A to x equals B? Well, isn't it the change in output over the change in input? So I could say it's my function value at B minus my function value at A divided by B minus A. Could I equivalently say it's F of A minus F of B as long as I write A minus B? It is the case, okay? If you're finding the slope of a line containing 2 points, it doesn't matter which function value you start with in your numerator, as long as in your denominator, you also start with that same value, that's partner. Do you kind of sort of remember that idea? So for example, suppose, can I just do a really side thing? What if I have 1, 3, and 2, 7? I'm going to pick some pretty chill numbers. Can you tell I like prime numbers? The one isn't, but anyway. Okay. So if I wanted to find my average rate of change between these 2 points, okay, we could start with this function value and subtract off that function value. But since I started with the 3 in my numerator, I've got to start with 3's partner in my denominator. What is 3 minus 7? -4. What is 1 minus 2? And a negative divided by negative is positive. Okay, but suppose Kiki's like, I don't want to start with a 3. I want to start with a 7. Okay, totally legit. You can start with the 7. It's the change in your outputs. But since I started with the 7 in my numerator, I need to start with 7's partner in my denominator. And what is 7 minus 3? 4. What is 2 minus 1? 1. And don't we get 4? Okay, so it doesn't matter which function value you start with, but you got to start with its corresponding partner in the denominator. Okay. So what if we have this function here? What if I want us to find the average rate of change from x equals negative 2 to x equals 1? Now I'm going to ask for participation. And I'm just going to posit it by saying it doesn't matter if it's wrong. Okay. Yeah, remove ego. We're here to learn. Okay. Well, first off, if I'm going to use my formula to find my average rate of change, what I need to do is find the difference between my function values, don't I? Again, it doesn't matter whether I start with negative 2 or 1. Who would you like me to start with right now? Negative 2. Okay. So what I'm going to compute is f of negative 2 minus f of 1. And then I divide by negative 2 minus 1. Do you all see how I'm plugging that in? Awesome. All right. My denominator at this point I can deal with. What's negative 2 minus 1? Negative 3. Okay. I need to do a little bit of work though in order to do my numerator, right? Because I don't know my function value at negative 2 yet. And I don't know my function value at 1 yet. But can I find them? Totally. Okay. How do we do that? Well, let's plug in negative 2 and let's plug in 1 and see what happens. Well, if this is how my function's defined, when I plug negative 2 in, isn't it 5 times negative 2 plus 7? So what comes out? Negative 3. If I plug in x equals 1, that's 5 times 1 plus 7. What comes out here? 12. Now I can go back and do this. I just need to be sure I keep my order correct. So I'm starting with my function value at negative 2. That's negative 3 minus 12 over that negative 3. So what do we get? We get negative 15 over negative 3 or 5. Now, I don't know how much you remember about lines, okay? But notice 5, 5. This is the slope of a line. Do you remember like rise over run? Rate of change. Notice we got precisely the slope of our line. And one would hope that with the line, I mean, the characteristic of a line is that it has a constant rate of change, okay? So this shouldn't be too much of a surprise. And we'll really see that nailed in as we proceed. 5 is the slope. Do you remember? And if you don't, it doesn't matter. Okay. Do you remember ever learning y equals mx plus b? Okay. M is your slope. That's my rate of change. Okay. We'll really get into this in chapter 2. We like lines. Don't you love how I tell you what we like? You will like this. Okay. Okay. It reminds me of being a kid. You know, my parents would cook stuff for dinner and just assume I'm going to eat it. You're going to like it. It's like, you know, well, eat it. It's like, I don't like this. Why would I eat it? And then they say, well, we eat it. And it's like, well, you wouldn't cook something you didn't like, for goodness sakes, right? You're the one who has the control. Anyway. Alas. My rule with my kids is if you don't like what I make for dinner, make something else yourself. All right, so now we're going to take a cuter looking function and we're going to find the average rate of change from x equals 0 to x equals 3. Okay, so what would I do? Well, notice I need my function values there, don't I? It's always really sweet when you're given your function values because it just saves work. And that's always really nice. Can I find my function value at 0 and my function value at 3? Yes. Thanks for believing in me. If I plug in x equals 0, this is the sweet one. Always enjoy plugging 0 in. You get -1. I just love that, right? Because once you plug zeros in here, bye-bye. Okay, G of 3 is going to take a little more work. We have 3 squared plus 2 times 3 minus 1. And we get 14 out. All right, you ready to rock and roll? Can find our function value at 3 minus my function value at 0 divided by 3 minus 0. What's my function value at 3? 14. My function value at 0 is -1. We know minus a negative is plus a positive. So we get 15 over 3, which is 5. That's not always going to be your rate of change. That's just, I guess, our number for today. Okay. What if I take my same function here, but now I'll just rewrite it. Now let's find the average rate of change from 0 to b. All right. Do you agree I need to find my function value at 0 and my function value at b? It's a little anticlimactic, but I'm actually going somewhere with this. We already saw that if we plug in x equals 0, -1 is going to come out. What if I plug in b? B squared plus 2b minus 1. All we did is change our variable. Do you agree we're going to find g of b minus g of 0 over b minus 0? Average rate of change. Okay. This might not look very satisfying, but deal. Okay. G of b is b squared plus 2b minus 1. Minus g of 0. What is g of 0? -1. And b minus 0 is b. Do you agree that minus a negative is plus a positive? So what do I end up with in my numerator? What happens to -1 and 1? They do. Aren't I left with b squared plus 2b over b? Can I simplify that? Notice I can pull out a common factor in my numerator, can't I? Don't they have a b in common? If I pull a b out of my first term, well, I started with 2, I pulled out 1, I got 1 left. And if I pull a b out of my second term, I'm left with 2. Do you remember pulling out greatest common factors? If you don't, you got to tell me now, like vaguely. Okay, I'll go into this in a second. When you're multiplying in a numerator and denominator, those cancel and you're left with b plus 2. But let me diverge here. If I have, do you remember your distributive property? Like if you have 3 times the quantity x plus 1, how do you get rid of your parentheses?
3x plus 3.
Yep. Everybody gets sum of 3. So you take 3 times your first term plus 3 times your second term. You agree? Okay. And if I have like x cubed times x plus 2, if I distribute, what would come out? Well, what's x cubed times x? When you multiply 2 things with the same base, what do you do to your exponents? You add them. And then if you need a review of exponents, I can do that for you, if that would be helpful, because it's really helpful to know those. We can do that on Monday if anyone would like. Okay, so this is our distributive property. You kind of sort of remember it, right? Okay, what we're wanting to do now is start on our right side and get to the left side. In other words, look at these 2 terms. What do they both have in common? They both have a 3 in common. So now we're going to pretend we're starting out with 3x plus 3. So I can pull that out. Well, when you're pulling something out, you're essentially dividing by it. So what is 3x divided by 3? Well, your 3's cancel, and what are you left with? X. And what's any number divided by itself? 1. So what we did over here is we factored out our common factor in our numerator. What do these 2 terms have in common? They got a b. So if I divide by b, well, I started with 2 b's. I took away 1. I have 1 left. And if I take 2b over b, aren't I left with a 2? And then I canceled out my b's using properties of fractions. Does that kind of ring a bell a little bit better?
Yeah. It's more clear.
Cool. Okay, so similarly here with x to the 4th plus 2x cubed, if I wanted to factor out my common factors, please, my friends, ask me these questions, okay? Like, please, if you need a reminder with properties of exponents, like anything, you gotta ask, okay? It's assumed in this class, but I think assuming is about one of the most dangerous things one can do in life, right? We all get into problems when we make assumptions. So what do these 2 terms have in common? Not only that, but I claim 3 x's, right? This one has x to the 4th power. There's 4 of them. This has 3 of them. So can't I pull out 3 x's here? You got it. So if I divide my first term by x cubed, when you divide 2 things with the same base, what do you do to your exponents? You subtract 4 minus 3 is 1, or x. And if I divide my second term by x cubed, those cancel. I'm left with plus 2. Is this bringing it back? Okay, so I don't want to do my next example because I don't have time, but I'm going to give you, I can't wait. Do you want to know foreshadowing what we're going to do on Monday? So given this function, x squared plus 2x minus 1. Let me make sure I'm remembering it correctly. We're going to find the average rate of change from x to x plus h. And this might look like, okay, Lauren, you're boring us with stupid gobbledygook, right? This is like a math book problem that's totally stupid. We're actually, when we compute this average rate of change, we're actually going to be doing calculus. When you find the average rate of change of a function, you're taking the derivative of the function. Fortunately, there are shortcuts, but you don't ever appreciate a shortcut until you have to deal with it the long way. Okay, but this is where we're going next time. So I'm not saying that so you don't come to class on Monday like, I don't think I want to see that, but that's where we'll leave off. So no homework in 1.3 yet, unless you want to work ahead. But what I will say is, please make sure you finish 1.1 by midnight tonight. And if you have time to get into 1.2 over the weekend, that would be awesome. Thanks.
Thank you.